Hi guys, in this video we will look at section C and D and perhaps more in the stereochemistry outline. With section C we'll introduce the very important idea of Fischer projections. This will be somewhat analogous to our Newman projections which we drew during test 1 material. It's a different type of way to draw a compound showing the stereochemistry other than the standard perspective drawing like these are here. Fischer projections, very important for organic chemistry. You will also see them in biochemistry whenever you look at carbohydrates. And that's shown on one of the handout pages in the other handout. These are all Fischer projections of carbohydrates such as glucose. Okay, but I'll begin by asking you to assign R or S configuration to the chiral carbon of each compound below. Now hopefully you've already looked at this, but we can do this. If we determine priorities, it's going to be what? Chlorine, F, then carbon, and then H is the lowest priority group. But we'll notice that the low priority group is neither in the back or in the front. If the low priority group is in the front, we learned that we can just do our clockwise or counterclockwise and then just reverse it. But what if the low priority group is in the plane, like in this case? Well, you actually have to, it's a bit more complex. We're going to have to either rotate the molecule or rotate our view. Now, most textbooks or many textbooks will try to teach you how to rotate the molecule. Now, I'm going to effectively do that in what I show you, but I'm first going to sort of change the view. And the first thing I would do here is actually show this compound in a Fischer projection. Now, with a Fischer projection, we're going to draw crosshairs. Okay? Something like this. And this is going to be the tetrahedral carbon. But this looks like a 90-degree bond angle around each of these bonds. Okay? Whenever we see a crosshair, first off, that means it's a Fischer projection, but this is equivalent to having this carbon here. And the bonds at the top and bottom, the groups going up and down, okay, these are going back. And the groups to the side are going forward. Sort of like if we envision a person kind of standing here and their arms are reaching forward to hug you. Now, thus, we can clarify that by having, okay, there's a carbon here. I'm not going to draw a C, but just a location. These are going back, so this bond is actually projected like that. And this bond is also projected back. And the ones on the sides are coming forward. And so whenever you see the crosshair, this is what it indicates. We assume that the crosshair, we correctly assume that the crosshair means this. Now note that actually there's nothing in the plane. we got 2 forward and 2 back. Now it can still be tetrahedral, yes, but if we had a model, okay, I could show this. All right. Let me put another one here. Okay. It's as if it's being held like this. If the plane was here, how can I show like this? Well, I'll hold it up. Okay. I'm actually going to hold it like this because these two are going back and these two are coming forward. But that's as if the plane of paper was sort of here. I can't, okay, here, plane in my hand. These two are actually coming up off my hand. You see how they're coming off my hand? They're not flat on my hand. Here we go. There's the plane going through there, the fingers. These two are coming this way, and those two are going that way. None of the bonds are projected in the plane of my hand or fingers. Okay, we can draw that like that. That's what the Fischer projection means. The things on the sides are hugging you, coming forward. On the board, it would be, you know, you'd be looking at it face on. Okay. Fischer, spelled with a C. Now that's just one crosshair. We could ultimately have maybe compound with, you know, 3 crosshairs. And each carbon here is tetrahedral. And we have again implied stereochemistry. These 2 bonds coming forward, 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 and the top and bottom going back. Okay, let's draw a Fischer projection of this molecule here. Now, here we go. First off, the molecule is here. Black going straight up, carbon, H in the plane. Okay. Red going back, fluorine. Green coming forward, chlorine. But if I draw a Fischer projection, I'm going to have something going straight up. Yes, it's going back, but it's also going up and back, down and back. And the other 2 groups are going to be to the right and left. Now, let me first show it on paper, not the model. And the 2 groups on the sides are also coming towards us. Now, my recommendation in doing this, always put the groups with the dashed and bold on the sides. That's the way I will always do it. We'll learn how to rotate this. Dashed and bold on the sides, and they're coming towards us. So I want to stand over here and look through there. Okay? I want to look through here. Stand over here and look through there. What am I seeing? Well, let me just turn and show you what I'm seeing. That's what I'm seeing. But the molecule's positioned like this, so I have to come over here and look. That's what I'm doing when I draw my little person there. Now in class I do this and I can't move the board. So what I draw on the board is fixed. But while holding it, I can move it and I can show you what I'm seeing. Okay? Now, here, the green is on the right. Right of my view, and the red is on the left. Chlorine green, fluorine left. Okay? And that methyl is going straight up. Yes, it's going back. That's back. And the H is going down, but it's also going a little bit back. You see, but basically this is straight down, but the H is back here. Okay? I'm going to clarify that as methyl. The methyl's going straight up, the H is going straight down. Now when I say straight, I mean, okay, straight down and back, as opposed to, okay, when I say straight down, I mean this, or if I can draw something straight down, all right, that's straight down as opposed to maybe that. Yes, it's going back, but it's straight down and back. And the chlorine green is on the right, and the fluorine red is on the left. That's what I see when I'm standing over there. But now it's in a Fischer projection. This is the same, and I'm just going to like do this. All right, this is a perspective, and this is a Fischer. Same molecule though. Now let's take the time to make sure we understand it's the same. First off, yes, it's a carbon with a methyl, an F, a chlorine, and an H attached. A carbon with a methyl, F, chlorine, and H attached. Now, R and S. Well, if we did R and S there, we would be doing it in a difficult manner. Let's do it here. Chlorine is 1, F is 2, carbon is 3. This is clockwise. The H is going back because in a Fischer with something coming straight down means it's going back. And 1, 2, 3 is clockwise. That's R. Okay. Now I'm not going to show you that this is R because then that means we would be able to do it without rotating our view. It's hard to see it's R. But we did 2 steps. Okay. We first convert to Fischer projection. That's what we're doing first here. And by converting to Fischer projection, we're changing our view, or at the same time, we're changing the drawing by changing our view. Now we have a better drawing, and now the H is either forward or back. It's no longer in the plane. Once it's back, it's very easy to do R or S. Now, let's do the other molecule. One chiral carbon. Do Fischer with one chiral carbon. We want to stand over here and look through there, because we want the things on the sides to be coming towards us. The groups on the sides are coming towards us. We need to be over here. Methyl's going straight up in the plane, H is in the plane, F is going back. Chlorine's coming forward. If I stand over here, okay, if I'm sitting over here looking through there, okay, like that's my face or something, I'm looking through there, what do I see? Well, let me turn in and show you what I see. That's what I see. And I see a chlorine on my left and a fluorine on my right. A chlorine on my left, a fluorine on my right. I see a methyl going straight up. Okay, but it's also going back. because that's straight up in the plane, that's straight up and back, and the H is coming down, but it's also going a little bit back. For it to be coming straight down but into plane, it would be like that. There's the Fischer view. All right, this is a Fischer of that. Now we also have recognized that these two perspectives are mirror images of each other. If we can determine this is R, we know this is S. But it's much easier to do it here because now chlorine's 1, fluorine's 2, carbon is 3. 1, 2, 3, counterclockwise. Low priority group is going back, counterclockwise S. Now we can also look at the Fischers, and you see how they are mirroring each other. Okay, let's review. What have we showed here? How to do R and S when the low priority group is in the plane. Your book will give you various recommendations. I'm recommending to look at it from the side and redraw it. And effectively, when you redraw it with a crosshair, you are showing a Fischer projection. Now let's start over, and now let's do R and S, and it's much easier because now the H has been positioned to be back, or something else, and we can rotate it or something. But now it's repositioned, in this case back. That's good because then we can just do priorities 1, 2, 3. We see it's clockwise with the low priority group back, that is R. And this one over here ended up being S. Okay, let's move to D. Compounds with more than one chiral carbon. Such as here, and we have 2 chiral carbons, the second and third carbons. First off, a very helpful formula. The maximum number of stereoisomers possible for a compound is equal to 2 to the nth power, where n is the number of stereogenic sites in the molecule. Now, a stereogenic site can be a chiral carbon or a stereogenic alkene. Note that I'm calling it a site. I'm not saying a stereogenic atom, because an alkene consists of 2 atoms, yet the alkene is just one stereogenic site. But a chiral carbon is another type of stereogenic site. How many stereogenic sites in this molecule? 2. Okay? Chiral carbon there and chiral carbon here. 2. It's always 2, but then to the second power equals 4 stereoisomers possible. But we got to be careful. That is a maximum number. Okay? Could be less. Could be less than max. Up here, how many stereogenic sites up here in this molecule? 1. 2 to the 1 equals 2. And we drew the 2. 1 is R, 1 is S. You cannot, there's not 3, there's not 4. 2 is the maximum number, and we drew them. Let's draw the 4 possible ones here. Now this is actually kind of set up for us on a page back here. same molecule. This is going to be our 4 stereoisomers. And we can draw maybe the OH bolded. All right. And how about the chlorine bolded? We can draw the OH dashed. And maybe the chlorine dashed. We could draw the OH dashed. I'm sorry, let's draw this one bolded. And the chlorine dashed. Is there a 4th way to do this? What about the OH dashed and the chlorine bolded? Is there another way? No. 2 to the 2nd power. Basically, that gives us 4 different variants that are possible when you have 2 variable origins there. All right. Let's do R and S real quick before we move to Fischer. We can do that here. For example, this carbon here, the low priority group is the H and it's in the back. Oxygen's 1. Carbon with these other groups or carbon with just H's? Well, it would be carbon with these other groups. Then the carbon with just H's. H is in the back. That configuration there is R. Here, this carbon, chlorine 1. Carbon with other groups is going to be 2. Carbon with only H's is going to be 3. H is in the back. Low priority group is in the back. This is also R. Okay. Now from there you can do the others real quick. Okay, I'll race you. Here we go. S, S, R, S, S, R. There we go. Right? Because if the backbone's the same and we just switch to projection, that goes to S. So both projections were switched. Here, well, that's the same projection as this. The projection with that carbon's been switched. And then going from here to here, they're both switched. And so after I worked to establish the configurations of the first 2, I could just cheat. And you see that's 4 different possibilities. That's an RR compound. That's an SS. That's an RS. That's an SR. In this case, they're all 4 different. Now we got to be careful. Down below, we may see that some of these may actually be the same, but these are different. Let's prove that to ourselves. Now these are all, assuming they're different, they're all stereoisomers of 2-chloro-3-hydroxybutane. They all have the same exact name. Because they all have the same connectivity, they just have different projections in space. Alright, so all that's kind of reviewed. Let's draw Fischer projections. Remember, the things that are dashed or bold, those are going to be on the side. Typically, your carbon backbone, top and bottom. Now, either end can be the top. I'm going to label the ground as here. We're looking at this molecule. Here's the ground. I'm going to stand here on the ground, my feet on the ground, and look through here. What do I see? All right. I'm going to clarify these as methyl groups. If I'm over here, the methyl's going away from me. All right? It's also going up. Because this is my view here. Standing on the ground. It's going up. Okay? It's going away from me. That means I can say it's going back compared to my view. It's also going up. Now when we say this is going up, we're not saying how much it's going up. Okay? But it is going straight up. That's going straight up. Basically, the methyl is going up and away. Now, if I turn this and come over here, where I'm standing, that methyl's going away from me. Here it is. Okay? It's away from the little man view here. But if I'm over here, that OH is bolded. You see it's bolded? It's coming off the paper, like my finger. If I'm over here, that finger's to my left. I'm going to do it. You need to look at it. Check your textbook, ask questions, let's do it, and then see what we need to explain. Methyl going away, OH on the left. There's an undrawn H there. We always want to draw in our H's in Fischer projections. Alright. Now we want to look at this methyl. For it to be going away, I need to come over here and be looking through here. With it going away, with the methyl going away, okay, the chlorine is on my right. Undrawn H on the left. Methyl going away. Chlorine is bolded, it's coming off the paper. Okay? Right now it's coming forward. If I'm over here, what do I see? I'll show you what I see. I see that. Chlorine to my right. There's that one there. Okay. From there I could actually cheat, but I'm not going to do that because I'm going to try to more walk you through how to do this. Okay. With methyl going away, the OH is going back. Alright. Well, if I'm over here and the methyl is going back, I mean the OH is going back, it's behind the paper. It's going behind the paper. If I'm over here looking, behind the paper would be to my right or left. Well, let's just turn everything. I'm over here where the pen is, okay? The pen is me. If I'm looking through here and something's going back, okay, behind the paper, I'm just going to turn and what do I see? Behind the paper is to the right. If I'm over here, behind the paper is to my right. I invite you to stand over here, stand at the board over here. If something's going behind the board and you're over here, that thing going back behind the board would be on your right. With the methyl going away, which that's what that means, methyl going away, top and bottom going away, the OH is on the right. With the bottom methyl going away, chlorine's going behind the board. If you're only over here and something's going behind the board, that's going to be on your left. The methyl going away, the chlorine's on your left. Undrawn H, there was an undrawn H there. There you go. Okay, let's look at these two. First off, before I drew all over them, we can see that they are enantiomers. Okay? Because what's the enantiomer of RR? These are enantiomers. Now they're not drawn exactly as mirrored. You can actually see them mirroring better in the Fischer projection. Do you see how these are mirroring each other? Enantiomers can also be called a DL pair. Because we know with enantiomers, one will rotate light to the left and one will rotate light to the right. I don't know which is which. I don't know which is D or which is L. But one of them is D and one of them is L. A pair of enantiomers is often referred to as a DL pair. Now this particular set of enantiomers is called 3O. Now 3O is when the high priority groups on the sides. Now what are the high priority groups on the sides? OH or H? Well, OH beats H. Chlorine or H? Chlorine beats H. So on each carbon, what's a high priority group? On this carbon it's OH, on this carbon it's chlorine. When the high priority groups are on opposite sides in the Fischer projection, it's called 3O. Okay, this is 3O. Well, what about this one? Well, the OH is high priority on that carbon, and on this carbon the chlorine, and they're both 3O. And I can add that the mirror image of 3O is 3O. Okay, let's try the other two here. Fischer projection, I'll consistently have the OH being upper, that is the chlorine closer to the ground. All right. I'm looking through here. With this methyl going away, I stand here so the methyl's going away. This is really what I see. I see a methyl going away. With the methyl going away, the OH is on my left. Undrawn H on the right. With this methyl going away, the chlorine is on my left. Undrawn H on my right with the methyl going away. Here's this compound in a Fischer projection. With the methyl going away, the OH is on my right. Undrawn H there. With the methyl going away. See? That methyl's going away. I'm over here. If I turn it, methyl going away, well, that chlorine's coming off the front of the paper. The front of the paper is now to the right. Okay? If I'm over here, the chlorine's going to my right. It's as if I'm on the left side of the board and something's coming off the board. Okay? Here we go. Here's the board I wrote on and something's projected off of it. If I come over here and stand and look at that, this pen is going to my right. If I come over here and stand so the methyl is going away, when the methyl is going away from me, the chlorine's on the right. When the methyl is going away from me, the chlorine's on the right. And there's an undrawn H going back, it would be on my left. Here are those two compounds in Fischer projections. You will see that these are mirroring each other. Well, just like this. What's the mirror image of RS? SR. They're both 2-chloro-3-hydroxybutane. They're stereoisomers. They are enantiomers. We see them mirroring here. This is a second DL pair. But this DL pair is known as erythro because the two high priority groups okay, the high priority groups same side in Fischer. 3O is your high priority groups opposite sides in Fischer. Now, how do I remember that? If you draw a capital E, you draw a line and then each of the other three lines are on the same side. But if you draw a capital T, you start with the same line, but you put one half a line on one side and one half a line on the other. Be careful. When you do the EZ terminology for alkenes, E actually means opposite. And there, E is a vowel just like the O of opposite is a vowel. And Z is the same side. This E is actually same side in Fischer, so don't confuse your E's. So this compound can actually exist as two different DL pairs for a total of 4 stereoisomers. Okay? But we already knew that. Remember, didn't we say 4? Yes, 2 to the 2 equals 4. We drew them. Now, let's repeat this process, but for this compound, replacing the chlorine with another OH, this is 2,3-dihydroxybutane. I'm going to go through and do this. You can just watch. I'm going to do it the same as up here. I had a bolded OH, a bolded chlorine. I'm going to change that there. Okay, a dashed, bolded, dashed, and bolded. 4 possible perspectives. We got 2 chiral carbons. Everybody agree that those are chiral carbons? This carbon has an OH, a methyl, a carbon with lots of stuff on it, and an undrawn H. Same thing over here. 2 to the 2 equals 4 stereoisomers max. Alright. We can do Fischer's. Now I can just fill these in the same as above. Methyl, methyl, OH, H, H, and instead of chlorine, make that OH. So I can go through and do that. All right. But if we turn over, I have a page that already has the top and thus the bottom completed. All right. Now I actually messed up. I didn't mean to include this in the handout. I don't think. This is brand new. Usually I do this on the board. I do all this on the board, but I have recently put in sort of this framework here to kind of work on, starting points here. But I also included sort of the answer, the summary answer here. Let's skip right to the complete story for down below. And what we have is the same thing I would have drawn if I kept going over here. The only difference between this and above is we replaced that chlorine with another OH. But you see that this compound here is the same as this one here. Just replace this chlorine with an OH. All right, looks like 4 different compounds. Indeed, this is a DL pair. And indeed, the OHs are on opposite sides in the Fischer projection, and that is 3O. But if we look at these two, this is actually not a DL pair. In this case, these two, it's the same compound. Now, by the way, this is RS, and this is SR. But these are the same compound. Okay, same compound. Yes, these are mirroring each other. The mirror image of RS is SR. Everything's got a mirror image. That doesn't mean they're different. Ultimately, the reason these two compounds are the same, or the way you can tell they're the same, is there's a plane of symmetry here. Internal plane of symmetry. Or sometimes it's called an internal mirror plane. And hopefully in the first video on stereochemistry, we mentioned that if something has a mirror plane, it's not going to be chiral. And I think we may have mentioned about finding Waldo. We will look for mirror planes. It's much easier to see mirror planes in Fischer projections. Okay? We can see the mirror plane here. If you just look here, it's harder to see. Although I can give you a little trick. What's the mirror of R? S. What you have here is you have two identical carbons. This carbon has an OH, a methyl, and the other thing. This carbon has an OH, a methyl, and the other thing, which is exactly like the other thing from this side. And the mirror image of R is S. Now over here, this was RR. Is that a mirror plane? Well, on one side you have a carbon OH methyl, on the other side you have a carbon OH methyl, but they're not mirroring each other. If R looks in the mirror, it doesn't see R. It should be seeing S. It's not a mirror plane. Now we can see that more easily if we draw it in a Fischer. And I can ask, is this a mirror plane? Is the top half mirroring the bottom half? And the answer is no. And if a compound does not have a mirror plane, the mirror image is going to be different. And we call that mirror image an enantiomer. These are enantiomers. This compound, though, does have a mirror plane, and the mirror image is the same thing. Okay? Now this compound, the high priority groups are on the same side, but because it has a mirror plane and the mirror image is the same thing, we, instead of calling it erythro, we call it meso. And this compound has chiral carbons, but it's not chiral as a whole. Okay, that is, the compound is achiral, even though it has 2 chiral carbons. So this is really not right. It depends on what you mean by perspective drawing. Okay, 2 to the 2 equals 4 max. But this is a case where we have less than max. Instead of 4, we only have 3. We have 1 DL pair, and then we have a meso compound. That is, if you were presenting this as different compounds, that's all you would show. Okay? You would show those 3. You wouldn't show 3 and then say, oh, by the way, let me show you one of those in a different way. Why would you do that? All right. Now, the relationship between these two are or enantiomers. What's the relationship between these two? This is SS. What's the relationship between an SS compound and an RS compound? Are they mirror images? No, the mirror image of SS is RR. That's the mirror image of this compound. First off, are these stereoisomers? Yes, these are both 2,3-dihydroxybutane. This is SS, that's RS. These two are diastereomers. Diastereomers are a type of stereoisomer. Okay, they have a different 3D arrangement of the groups, but they're not mirror images. It's kind of like a default category. Stereoisomers that are not mirror images are called diastereomers. These two are examples of diastereomers. They have a diastereomeric relationship. What's the relationship between these two compounds here? Well, those are identical. If you built a model of these two, you'll see that the model is the same thing. You can rotate this compound and it will superimpose with this compound. What else can we do here in this video? We've introduced Fischer's. We go back to now we can answer questions like number 4. How many total stereoisomers are possible for each of the 3 compounds above? All right. I see this is also a optical activity question. That was we covered that during the second stereochemistry lecture. All right. We're getting to a point where we should be able to answer just about all the questions here on this stereochemistry DQ page. We can also answer most all of these at the top on this warm-up page. All right, show this compound in the Fischer projections. The one thing I will still try to teach you is once we get a Fischer projection, okay, all right, something like this, we will be able to rotate this. All right, and I'll teach you how to rotate that. Because what if I ask you to draw this with the, I would never do that in this case, but what if I did, or what if you were asked to draw this with the OH and the chlorine at top and bottom? All right. Why don't I go ahead and do that? We can just rotate the top 3 like a clock dial. This can rotate up, this can rotate here, and the H can come here. Chlorine can rotate down, the methyl can rotate there, and the H over here. So if you wanted to put the OH and chlorine at top and bottom, OH at the top, the methyl rotates here, and the H here. The chlorine rotated down, it moves the methyl here, put the H here. All right. So these two are the same compound, we just rotated. All right, that's like here. I didn't rotate this bond coming down, like the red I'm holding. Or let me do this, okay? Here's the bond coming down. I just rotated the top 3. This is going straight up and back. But see, I can turn these 3 just like clock dial. Now the green is going up, okay? If you want to make the red go straight up and back, all right, like we did here, I made the OH go straight up and back. Look where the green goes, all right? Now the red is going up and back, but the green just rotated to the left. The OH went up. The methyl, which in my hand here was green, it just rotated to the left. Down below, like this, chlorine to the right, if I want to move that chlorine straight down and back, the group that's currently straight down and back moves to the left. The group that's currently straight down and back moves to the left. Okay? You can just rotate the top 3 and the bottom 3 and it'd still be the same molecule. I went ahead and did that here. Now, if you were asked to draw this, I would first draw it like this. Because again, the things that are dashed in bold on the sides. Then rotate. Okay, Please look at the remainder of this handout. We'll be finishing it up, including this page here. All right, definition of meso compounds, I kind of have already mentioned it. Finding plane symmetries, including on the warm-up page, and that will get us to these here. Identify each of the following as chiral, achiral, or meso, and ultimately we'll be looking for a plane of symmetry. I'll remind you back over here. The ultimate reason of why this compound is chiral is because it has no plane of symmetry. The one below, though, does have a plane of symmetry. Okay, I'll leave it here. Okay, need to work on understanding the various points, either from here, reading in your textbook. Okay guys, that finishes up this video on the introduction of Fischer projections, erythro and threo, meso compounds, etc.